Hello everyone, and welcome to today's webinar about how to maintain stable communication with your drone. My name is Amin. I'm Alpha Application Engineer at HFWorks. This is the breakdown of the presentation. So first we'll talk briefly about the drone and some of its components, as well as areas where drones are being used. Following that, antenna design challenges and some simulation results will be presented. At the end we have a live demo. So in case you have any question, I'll be happy to answer them at the end of the presentation. Alright, so let's talk about drones. What do you mean by drones? Drones refer to aerial vehicles without any human pilot, crew or passenger on board. They receive remote commands from a pilot or relies on software for autonomous flight. According to Grand View Research, the global commercial drone market was valued at $13.4 billion American dollars in 2020. According to the same study, North America accounted for the largest market share of around 37% in 2020, and it is anticipated to witness significant growth over the next couple of years due to advancement in drone technology and the growing demand from businesses across various industries. Now let's look at the key components of a drone. Drones have a large number of components, including electronic speed controllers, which controls the motor speed and direction, flight controller, a GPS module, a battery, antenna, receiver, cameras, sensors, including ultrasonic sensors and collision avoidance sensors. Last but not least, altimeter, which measures the altitude. As we can see from the image on the right hand side, the controller usually operates at 2.4 GHz range and will carry further than the live video feed signal, which operates on 5.8 GHz range. This means that you will lose your video feed long before the drone will lose connection with the controller. Telemetry module, which is used to get flight details such as speed, elevation, battery level, and all the important data that you can use to keep track of your overall flight performance. As you can see, for the drone we have 3 antennas which operate at 3 different frequency range, namely 433 MHz, 2.4 GHz and 5.8 GHz. Alright, so let's look at areas where drones are being used. Drones are used for more than military and recreational purposes. In fact, they can be found improving the efficiency and safety of almost every industry that we could imagine, from wildlife conservation to medical supply delivery. Probably the oldest, most well-known use of drone is in military. So for example, they can be used as intelligence gathering tools as well as for airstrikes. Delivery is another area where drones are being used. Retailers and the grocery chains have started turning to drones as more efficient delivery alternative instead of relying on delivery drivers, which sometimes are inefficient. Delivery drones can be used to transport food, packages, or goods to your front doorstep. Drone can also be used for emergency purposes. Sometimes it's not safe enough to send humans into risky situations due to the severity of disaster. For example, if there is an avalanche, drones are deployed to look for those caught in the snow. Moreover, they can be used for fighting fires. The K-Max has already been used in China and Australia to assist in fighting fires. Agriculture is another area which benefit from advancement in drone technology. So for example, they can be used for field surveys and seeding our fields. Last but not least, drone can also be used for wildlife and historical conservation. For instance, they can be utilized to track animals as well as fighting against poaching efforts. So now let's look about the operating range of drones. How far a drone can fly from the controller while still maintaining good signal is called the drone range. A toy drone may have a range of about 50 to 100 meters, while mid-level consumer drones will typically have a range of about 100 meters to 3 kilometers. High-end consumer drone can have range of about 5 to 15 kilometers. On the right, we have a table that illustrates operating range of different commercial drones. We can observe from the table that the drones have an average flying time of about 30 minutes. Now let's look at some practical ways to increase the range of our drones. Setting firmware setting to FCC rather than CE limits can help getting the best possible operating range. Using powerful receivers and range extender can also result in significant jump in operating range. So far we have talked about the drone, some of its key components as well as areas where they are being used. So let's talk about the antenna design challenges, which is the main focus of today's webinar. Just like any radio control device, drones, quadcopters or UAVs requires antennas for their functioning. For successful operation of the drone mission, the communication between the drone and the remote control must be stable to avoid losing the drone. Mounting the antenna on a drone is a real challenge. The antenna cannot be located at the center of the drone and either cannot be installed close to the wings because of the noise with the circuitry. It is preferable to locate the antenna in the middle of the wing where interferences are fewer. The antenna should be low profile to diminish aerial vehicle drag problem when the drone are flying. To avoid losing the drone, stable communication must be maintained between the remote control and the drone. One way to achieve this is by installing antenna in each arm of the drone to add spatial diversity to the system. The drone body frame can have effect on the overall performance of the antenna. For example, the motor which are made of metals can cause reflection for the transmitted signal, which in turn influence the antenna radiation. As we can see, there are several parameters that must be considered to ensure proper operation of the drone. Therefore, 3D electromagnetic modeling is crucial before the real fabrication of the antenna. Today we'll be looking at 3 antenna configuration. So first we'll look at the antenna isolated, which has a flat surface. Next we'll try to see the performance of the antenna when its structure is bent. Last we'll be looking at the performance of the antenna on a drone. Alright, so let's start with the wire-rounded shape antenna which has flat surface. The antenna is made of copper. As for the substrate, low loss material 5850 LZ is being used. The antenna has a total dimension of 39 mm by 29 mm by 1.27 mm. On the right, you can see the top view and the bottom view of the antenna. The bottom view corresponds with the ground plane. 50 ohm SMA connector is used for feeding the antenna. So let's look at some of the simulation results. On the right, we have an electric field animation. On the left, we have a parametric study which is used to study the effect of changing the circle radii of the circular element. So if you remember from the previous slide, we have the circular element just at the center of the antenna. As we can see from this graph, that increasing the radius of the circular element helps to improve the reflection coefficient as well as the bandwidth. Alright, so let's look what would happen to the antenna if we try to bend its structure. So looking from left to right, so we have top view, in the middle we have the bottom view, on the right we have the front view. So we can see the concave shape of the antenna as well as the 50 ohm SMA connector. So for each antenna, the thing to look for each antenna is of course the reflection coefficient. So by bending the antenna structure, we can see there is a shift in terms of the resonant frequency, but still the radiation at 5.8 is still under -10 dB. So let's look at the radiation of the antenna. On the left, we can see that the antenna has a maximum gain which is directed towards the ground and has maximum gain of 4 dB. Such kind of radiation will be useful especially if we are doing 3D mapping using drones. In HFWorks, we have what we call the antenna far field parameters. Under this table, we can see different antenna parameters such as maximum directivity, maximum gain, radiation efficiency, and total efficiency. On the left, we can see the 2D radiation pattern at phi equal to 0 degree. So we can see again the maximum radiation is towards the ground. Alright, so let's see what would happen if we place the antenna on a drone. On the right, we can see 4 antennas which are placed on a drone. The drone body frame is made of plastic. The same thing for the blade. As for the motors, they are modeled using perfect electric conductor or PEC. On the right, we have an animation of the electric field for the 4 antennas. So first let's look at the reflection coefficient for the 4 antennas. As at 5.8 gigahertz, we can see that the 4 antennas have reflection coefficient which is less than -10 dB. When we have antennas that are operating near each other, the next parameter to look for is the coupling coefficient. So basically, we want to make sure that the antenna are well isolated so that they cannot affect each other radiation. So looking at the coupling coefficient graph on the left, we can see that the antenna are well isolated and the coupling coefficient are less than -30 dB. So let's look at the 3D radiation pattern of the antenna. On the right, we can see there is slight change in terms of the 3D radiation pattern as compared with the previous case. And the reason for this is that for the drone body frame, it doesn't have much effect on radiation due to the low permittivity of the plastic. The motors which are modeled using perfect electric conductor, they can have an effect on radiation, but since they are far from the antenna, so basically they don't affect the radiation, especially in direction of -z axis or towards the ground. On the left, we can see the 2D radiation pattern of the 4 antennas at phi equal to 0 degree. So we can see that the 4 antennas have again radiation pattern, have maximum radiation which is directed toward the ground, and this will be useful for applications such as the 3D mapping. Now we'll have a live demo. I'll be showing you how to simulate such antennas using HFWorks. HFWorks is fully embedded in SolidWorks and is called certified by SolidWorks. So once you are done creating your geometry in SolidWorks, you can just go ahead and start your simulation in HFWorks. So it's simply just a tab. So basically you don't need to export any CAD. In HFWorks, we have 4 types of study. We have antennas, S parameter, TDR, and resonance. But today we'll focus on antennas. So for each study, basically we have 3 main steps. So first we need to specify the frequency range. So for example, here we have the start frequency, the end frequency, and number of frequencies. Also we can specify the type of frequency sweep, either discrete sweep, fast sweep, or single point. As for the mesh, we have manual mesh or adaptive mesh. Also we can do thermal analysis. So the next step is to apply material. So to apply material, so we just right click, we say apply material. In HFWorks we have a material library which consists of material from different vendors such as Mitsubishi and also Rogers. So once we apply material, next step is to set up the boundary conditions. So we have different boundary conditions such as port, lumped port, PEC, PMC, PEC symmetry, PMC symmetry, radiation boundary or absorbing boundary. Also we have a signal. Also, if you are interested in applying mesh control, you can just right click, say apply mesh control. You can apply mesh control on bodies, faces, or on edges. You can also specify the element size. Alright, so let's look at some of the simulation results. So before doing that, so let's look at some boundary conditions. So this is our port, and this is the signal. So we apply PEC on the patch and also on the ground. So for the air, maybe we need to show the air. So this is our radiation boundary. So let's look at some simulation results. So first let's look at the return loss. So we can see that the antenna almost resonates at 5.9 gigahertz. So to generate 2D plot, so we just right click and say 2D plot. So you can specify the study, and then you can after that we specify the parameters, and then we said add. So it's pretty handy. So let's look at the electric field. So to animate, we say right click and say animate. So you can clearly see the animation of the electric field. So next is the parameterization or parametric study. So for this study, we want to see the effect of changing the radius of the circular element. So once you finish specifying the minimum and the maximum range for the parameter that you want to study, next you need just to click and say generate scenarios. So for this study, we have 3 scenarios, as you can see. So let's look at the results. So we can see again that increasing the radius helps improve the return loss. So let's look at the second structure, which is the bent structure. So this is the antenna. So it's top view, and this is the bottom view, and this is the 50 ohm SMA connector, which is used to feed the antenna. Let's look at the reflection coefficient. So we can see that there is a shift in terms of the resonant frequency, but still the reflection coefficient is below -10 dB at 5.8 gigahertz. In HFWorks, we have, as I said, we have what we call antenna far field parameters. So you can see here different antenna parameters. You can also print versus current frequency or frequencies. Also you can export results to different formats such as text, CIT, SPC, or touchstone. So let's look at the 3D radiation pattern. So we can see that the antenna has maximum gain, which is directed towards the ground. The same conclusion can be drawn from the 2D radiation pattern. So let's look at the last scenario, which corresponds to the antenna when are placed on a drone. So you can see that 4 antennas on a drone. So as for the drone body frame, which is made of plastic, so you can see those are made of plastic. So for the motors are modeled using perfect electric conductor, PEC, as we can see, the blue ones. So let's look at some simulation results. So first let's start with the reflection coefficient. So we can clearly see that the reflection coefficient for the 4 ports are below -10 dB at 5.8 gigahertz. Next, let's look at the coupling coefficient. So we can see that at 5.8 the reflection coefficient is below -30 dB, which means that the ports are well isolated. So let's look at the radiation pattern. Let's start with the 3D radiation pattern. So we can see that the maximum gain is towards the ground, and this helps especially in 3D mapping applications. So from this plot we can see the 2D radiation pattern for the 4 antennas at phi equal to 0. So we can see that the 4 antennas, they have maximum radiation which is pointing towards the ground. So let's look at the electric field animation. So this is the drone. So to animate, again we say right click, say animate versus phase. So it's loading. So now we can clearly see the animation of the electric field. Sometimes when you come back from work and you want to run the studies overnight to save time, so either you said run all studies, or you can also select the study that you are interested in. In this case, for example, if I'm interested in those 4 studies, I select them, set run selection. So it's pretty handy. Here comes the end of the live demo. So to summarize, we have demonstrated you some of the drone antenna design challenges and showed you how easy and efficient HFWorks in solving these problems. You have learned that placing an antenna in the middle of the wing proves to have a good performance as interferences are fewer. Lastly, placing one antenna at each arm of the drone adds spatial diversity to the system, which helps maintain stable communication with the drone. With that, I would like to thank you, and now the floor is open for questions. Thanks. So if you have any question, I'll be happy to answer them now. As you can see in the chat, there's one question. So the question is why 5.8 gigahertz frequency is usually used for the drone video transmitter. Okay, Dagor, thanks for your question. So basically, like as you know, when we go high in frequency, this will make the antenna physically small. And the second reason is that when you work at 5.8, so we'll have a better quality image because of increased bandwidth. Last but not least is this to avoid interference. So for example, if we were to work on 2.4, so we'll have like more interference as there's so many devices working 2.4. Unlike 2.4, for 5.8, there are not as many devices that are working on that frequency. So that will help to avoid interference. So if you have any other question, I'd be happy to answer them. No, you're welcome. All right, seems there is no other question. So if you have any question, you can always contact us at emworks.com. So on behalf of EMWorks, I wish you a wonderful day. Thanks. Goodbye.